Hey guys, welcome back. So far we've taken a look at resting membrane potential and polarization. We've looked at the terms associated with polarization, depolarization, repolarization. Now we want to take a look at the membrane potentials. There's two types of membrane potentials. There's graded potential and there's action potential. Graded potential only occurs in the dendrites. Action potential occurs only in the axons. Graded potential is a short-lived, localized change in the membrane potential of a dendrite that can either result in a depolarization or a repolarization event. You can see those played out here in the graph. These changes cause local flows of current, but unlike the action potential, these local flows of current will weaken as they get further away from the site of stimulation, with their magnitude varying directly with the intensity and the strength of the stimulus. That means the stronger the stimulus, the stronger the graded potential will be along dendrites, and typically the increased number of dendrites that will actually be sending that electrical event. Now, as the membrane depolarizes, the sodium migrates inward, causing the potassium ions to be pushed away, just as we saw earlier. The combination results in a less negative cytoplasmic environment. This is effectively used by the dendrites to sum the electrical potential at the axonal hillock. Now remember, the axonal hillock is that funneling component that leads into the axon. If the electrical events are strong enough at the axonal hillock to sum at the axonal hillock, those electrical events can result in a summing effect that reaches threshold depolarization and results in an action potential that will be conducted down the axon. Thus, the closer the dendrite is to the hillock, the more effect it can have on that graded potential being converted into an action potential. The stronger the stimulus, the greater the chance of the summing occurring at the axonal hillock. The closer the dendrite is to the axonal hillock, the greater the influence it has. It is called graded because the ability to sum numerous dendritical electrical signals with the collective effect factoring in on the result at the axonal hillock. On the flip side, though, action potentials are quite different. Action potentials only occur on the axons, and action potentials are going to encompass a number of different events. But the first couple things I'd want you to know is an action potential only occurs on the axon. And once we have reached that threshold depolarization at the local level, at the axonal hillock, that electrical event will be conducted down that axon at the same strength the entire length. Much different than a graded, because remember, a graded weakens as it gets further away from its origination point. An action potential, though, is same strength. And typically in an axon, it's going to be unidirectional. That means it starts at one end and goes to the other. And that is simply because the axonal hillock is the beginning point of the axon, and the neuromuscular junction will be the end point. Now, if we want to sum up these events and lay them side by side, we would see that at the beginning we do have the resting state again. And at the resting state, all the ionic channels are closed, and we do have a net charge of a negative 70 millivolts. An electrical event or a chemical event comes along and causes a change in the membrane potential. That change in the membrane potential causes localized depolarization to occur. Now, localized depolarization is occurring because of the opening up of the sodium gates. If enough sodium moves in a given amount of time, we can reach what's called threshold depolarization. Typically, that's around a negative 55 millivolt charge. If we can reach a negative 55 millivolt depolarization state in a given amount of time, we see that localized depolarization results in a propagation or a spreading event occurring along the surface. This is what we call self-generating. And if the threshold is reached, depolarization becomes a self-generating or propagating event. In reality, what you're looking at is positive feedback mechanism, presence of sodium ions stimulating more gates to open, allowing the neuron to become 100 or 1,000 times more permeable to sodium than it would be at rest. Actually, this causes the neuron to overshoot the necessary 0 millivolt and actually obtain about a positive 30 millivolt before we can shut off and completely close off these sodium gates. Thus, the action in action potential is going to be this positive feedback mechanism. The propagation is going to be unidirectional, as I said. Now, the 0 millivolt charge during depolarization results in activation of a negative feedback mechanism that triggers close the sodium gates. Now, this is a different set of sodium gates. They're called inactivation gates. While this process is slow to occur, we do have the overshoot, but that same 0 millivolts is going to trigger open the potassium gates, and potassium is going to start to flux out of the cell and into the extracellular space. As it does so, it's going to make the inside of the cell less negative. That's an event we call repolarization. Now, repolarization, as we said, will go back to the resting state of a negative 70 millivolt. But once it hits that negative 7 millivolt, that will trigger closing of the potassium gates. They close a little bit quicker, but it still takes a moment or so. And so we see that the charge actually goes below the negative 70, somewhere around a negative 90 millivolt charge. It undershoots. And then at rest, we depend upon an ATP-dependent sodium-potassium pump to reestablish the ionic concentrations on either side. I hope that visual aid helps you to see the concepts around resting state, depolarization, repolarization, the concepts of overshooting, undershooting, hyperpolarization, hypopolarization, and threshold. You guys have a great day. Again, be safe, and I'll see you sometime soon.